I would like to introduce Associate Professor Dario Coronelli. He's from Polytechnic in Milan, civil in the Department of Civil Environmental Engineering. He's teaching assignments on the School of Architecture and Civil Engineering. Research topics include structural effects on corrosion in reinforced concrete and physical concrete structures, and historical masonry construction. His expertise include laboratory and real-scale testing, numerical modeling, seismic design assessment. He's co-governor of FIB Committee 3, existing concrete structures, TG 3.2, and a member of FIB TG 2.5, bond and material models, and SCI 364, rehabilitation of concrete structures, and SCI 421, design of reinforced concrete slabs. And Professor Coronelli has been running actually a big research project which is called the Slab Stress, that slab structural response for seismic design in Europe. That includes a full-scale testing of flat slab building for lateral and gravity loads in collaboration with EPFL and Lausanne and UNOVA in Lisbon, UTCB in Bucharest, and ELSA lab at Sparta. So with this, I introduce Professor Coronelli.
Thank you very much. Thank you for the chance to be here in this session honoring Professor Galli, and proceed with the presentation. Right. So slab stress is motivated by the lack of regulations in our European seismic code concerning flat slabs. We are using in Europe this term to indicate what North America is indicated with a flat plate, but our pre-normative documents are using this term. And we don't have it designed according to our European design. And to start with, we carried out an analysis of state of the art on flat slab frames in the literature, and we found that mainly with regard to scale tests, 30–40% for shaking table tests, or 40–50 for the cyclic tests on floors. There's only one real scale test on a frame that was designed though for just gravity load. So we were motivated also from this point of view to go for the real scale test we're going to see. Next slide, please. So the issues we examine are on the whole connected to the both global and local connection response up to failure. We examined different reinforcement layouts, integrity reinforcement, shear reinforcement, and also strengthening. The problem was aimed also to consider existing structures, as we have many structures designed with slabs in Europe, partly with national codes and partly just by sort of adapting general concepts to use them. Next slide, please. So this is the specimen that was tested, thank you. Tested in the European Commission lab in the Joint Research Center at ISPRA, that is specialized in these large-scale tests, real-scale tests, and also carrying out pseudodynamic hybrid tests simulating dynamic effects through a quasi-static loading and simulation of dynamic effects via a numerical simulation. So the features are, well, slab is 20 centimeter thick, spans 4.55 meters. We've got 3 different column sizes, interior 40 by 40, and then 35 edge, 30 corners. And yes, the actuators were placed in the middle of the side span, and you can see in the 3D drawing sketch. So materials, it was normal strength concrete, nominal 30 MPa, and ductile steel with a nominal 500 MPa yield. And the layout was for the longitudinal in two different layouts. In the western left side, we had smeared with regular spacing, whereas we have a concentrated layout in the eastern right side of the plan. And for the bottom reinforcement not shown, and especially for the integrity, we had a detail which is in Eurocode 2 of 2 bars crossing the column to provide support after failure in each direction. And another detail not shown in the drawing is the end anchorage on the edges were simple bends, because that is very common use in design in several countries. So we wanted to see the effect of that. And we wanted to test the efficiency of shear reinforcement. So we placed studs in the second floor slab. So for the design, the key concept was that we adopted concepts taken from the North American code, the ACI code. So we limited the gravity shear ratio. Approximately, it's 0.3 if you use, not using the capacity reduction factor, or with the capacity reduction factor is a 0.4 gravity shear ratio. And we'll see details later. And then we were checking that the drift ratio given by the seismic loading were below the drift capacity. That was evaluating using models that are being developed in Lausanne by Professor Muttoni in agreement also with the existing ACI code equations. Yes, so the testing program included both seismic and cyclic tests. So this slide is dedicated to the seismic that were simulated with the pseudodynamic hybrid technique I outlined previously. So the building design considered ductile shear wall as a main resistant, seismic resistant element, 2 walls in this case, as we see depicted in the plan. And these were simulated numerically within the pseudodynamic technique. And the physical frame was actually the 2-floor flat slab frame we described. 2 different signals, one for the serviceability limit state earthquake and one for the ultimate limit state earthquake, acceleration compatible with our code spectra. So yes, this is the scheme of the testing program. We have the PGAs of the 2 seismic tests, and also the outline. So the maximum drift in 2 different cyclic tests. Yes, here we have the history for the displacements shown. So we have 3 repetitions in the first test going up to 2.5, whereas just a single cycle for the 6% large amplitude test. In between the 2, we have a repair phase, which I'll describe in the following. This is a description of the gravity loading. Seismic loading required 3.6 additional kilonewton per square meter loading that brought the interior connections to 0.3 gravity shear ratio. And we adopted the same for half of the first floor slab and the whole second floor slab in the first cyclic test. We differentiated slightly the gravity loading in the first floor without transverse reinforcement because we wanted to test different gravity shear ratios. And then for the final cyclic test, cyclic 2, we wanted to use the same full loading, but because of reasons we shall see shortly, we were not able to load the whole plan, so we had to restrict the loading to part of the plan. Instrumentation, new feature is load cells were designed in order to obtain thermal force measurements within the columns. So steel profiles with strain gauges glued in order to then calibrate the cells and obtain internal forces. And then we had a set of inclinometers on the sides of the columns and on the columns, sorry, on the side, on the slab to the sides of the column and on the columns as well, top and bottom. And through slab crack measurement LVDTs to detect the punching crack development. So for the results, the seismic results were very much influenced by the stiffness of the virtual walls we designed. That was then related to a particular requirement that is in Eurocode for the primary system that should have a much larger system than what is the secondary system, in this case, the flat slab. So you can see that the drift ratio was quite low, and the physical frame was very, damage was very small, actually, just initial flexural cracking. So on the whole, that proved the design was definitely sound. We could say maybe we could have designed more deformable walls. So that then goes into the development of design rules for a combination of walls and flat slabs, according to what we have in the code now. We move on to the first cyclic test, where we have the global response. So this was up to 2.5 drift. The gradual loss of stiffness we know for the flat slab frame, and relatively low energy dissipation, but the reaching of a plateau with the development of plastic deformation up to the maximum drift and limited loss of resistance in the structure with the repetition of cycles. There were major events that occurred during this test. Next slide, please. That were related to the damage of the edge and corner connections that were very badly damaged. This is something that occurred in previous tests with different details at the edges. So American regulations specify a closed hoop at the edge, whereas we use these simple bends. But cracking is similar, but it was quite severe, and definitely signs of punching in these connections. We have here the local measurement of the connection response. So the instrumentation we saw allows to obtain the cycles. These are shown for interstory drift, but we also have all the measurements of local rotations, so they can be further developed. We see stable response of interior connections, one example, whereas definitely failure in the edge connection and the corner connection as well, approximately between 1.5 and 2% drift ratio. So this is the crack pattern on the first floor. It corresponds to what we've seen in the photographs, and relatively good condition of the interior and edge connections parallel to the loading, north and south sides. Next slide is the second floor that had definitely a lesser damage related to the presence of the shear reinforcement. And you can see more spread flexural cracking and torsional cracking around the connections. So after the first test, we proceeded to the pair of 3 connections in the first floor using bolts that were placed within holes drilled through the slab in the same pattern and with the same diameter of the studs in the second floor. And due to the damage of the edges, the choice was taken for safety reasons not to load half of the outer spans. And you can see the hatched interior part is loaded with the water tanks, whereas the outer part was not loaded, thus reducing the gravity shear ratio just on the edge and corner connections, which shows us the results for the 6% drift test, where we have initially an increase in the maximum force and sort of stable response up to the first -4% cycle, where a major event occurred with the punching of one connection, then followed by punching on the other side. And that started the loss of the load resistance of the structure through these last results. So these are results for the moment drift of all connections. You see the punching in the interior connection on the left. Red is for the second floor, and we see that there are a sign of failure in the edge and corner connections in the second floor as well. But these failures occurred for higher drifts than in the first floor, but with similar crack patterns due to torsion along the edges mainly, and drifts between 3% and 5%, where we see punching failure crack pattern in connection B2 and relative moment drift cycles. And here briefly conclusions. Behavior of the structure was stable beyond 2.5, so that gives us possibility to think of design rules for a range of drifts where primary seismic resistant systems such as walls, for example, would be active. The internal connection punching was within the range of drift capacities in the database based on scaled and isolated individual connections, probably towards the upper side of the gravity shear ratio that was there. There is a mistake there. The gravity shear ratio was 0.3, not 0.2. I apologize. With the mean value without the capacity reduction. Otherwise, it's at 0.4. Edge and corner connections failed earlier, as we've seen, with very severe damage, which must be considered very accurately for the existing structures we had that have been designed in such a fashion. The structure showed important distribution of load effects from the edges to the interior connections that provided the stable response we have observed. The integrity reinforcement was efficient. The slab did not fall from the supports despite severe damage it had undergone, with just simple 2x2 bottom bars through the columns. And positive performance of the floor with shear reinforcement and of the strength and the repaired connections as well, because we didn't compare these with the ones that failed, but the fact is that they had very limited damage compared to the non-reinforced ones. Thank you. I would like to show you a video of the punching failure, if I can share the screen, and we have a spare couple, well, it's just a minute. So this is a second cyclic test. You have the view of the interior connection that is going to punch. Okay, thank you.
Thank you very much. Great.